So when we start like tailings dam, I don't know how many people you are familiar with what is tailings dam? Is it a dam or it's a pond? So that concept is always, everybody thinks like it's a dam, like a hydro dam. Any dam is like a dam or it's a pond, but in reality it is a combination of dam and pond, mainly designed to store and contain mine waste material produced different type of mining operations. So these are the fine materials. Like in the mines we get waste product of big like rock dump, but these are mostly the fines. And in the initial phase, there is some change, but in the initial phase, how we can store these fines? So the fines were converted into a slurry product where we add like 60 to 70% of water into it and 30% solid. So that can easily take the material to a large distance through pipe. So they were taken by pipe and got deposited. But we have to see that they still contain, this slurry contains all kind of heavy metals and toxic materials and also acidic materials, which can be harmful if it is exposed to the environment. So that's the main thing. So that's why we cannot just let it go. In the past, like some people have told me that this slurry was diverted to a river, because the people think that yes, river is a big flow of water, but if you put slurry onto it, it will like dilute. But definitely that's not the case. So we have to make sure that this slurry thing stays inside. It should not go anywhere else. That's why we are designing a dam to store it. So dam will protect all the slurry material, and that is what called the tailings dam. So where are these tailings dam is being generated? You can see that the process in the mining, we have like crushing and grinding, refined fines, all our beneficiation process, we collect the fines, coal washing process, we collect the fines, and also the residues like ash and also slag, the combustion of coal and from the blast furnaces and also from the bauxite refining, we are also collecting the fines. And also a lot of plant, the chemical byproducts, they are also fines. The chemical reaction with a process like gypsum is also collect the fines. So these where the fines are generated. So you can see that the process. We start with the rock, and that rock contains minerals and metals, and they processed like with the dump truck, take them, and in the second process they were mixed with the mined ore is being fined and mixed with water. The process is to remove the mineral from the waste, and other material also extracted, remaining fines known as the waste product, and that in a slurry form, and finally it goes to the tailings pond, and that tailings pond is surrounded by a structure called the dams. Can we go to the next?
Just change. This one.
So this is kind of a picture which demonstrate most of the process, like how the in a mines we have overburden and then we have the ores, and those ores were taken by a dump truck, dumped into a like crusher, and then from the crusher it goes to the mill, and from the mill plant that finer waste is produced and it is stored in the tailings dam. You can see this is the dam structure, and there will be all these are the tailings along with the water is being stored in there. And the tailing process and also the waste rock, they are different because the larger material, waste rock which doesn't go to the crusher and the mines, they are also deposited as a waste dump. But from environmental point of view, the environmental consideration, the design is same. Again, these waste materials also contain a lot of acidic minerals and also some toxic minerals. That's why we also want that waste materials should not also come into the contact of the environment. What is the issue here? I mentioned that in 1960s we started somehow storing these tailings thing, and by 1980 they found some failure, and those failures created devastating process to the community, environment. Then the people think that, oh, it is a different thing, we have to again think about some kind of design technology. So that's why around 1980s all kinds of design technology developed, and with time you can see that between, this is a thing from 1915 to like almost in 100 years, we have seen a lot of failures, and these are the different what the cause of the failure, and we can see the better way the failure, because the failure of tailings dam is creating all these consideration, environmental consideration. Because if it is stable and it doesn't go to the outside or it doesn't interact with the environment, then everything is good. But when it fails, you can see that it is devastating. And one of the failure which we will discuss at the end is the Brumadinho failure. I want to focus that one because that failure changed the whole concept of design of tailings and also bring that global industrial standard. Why is that? Because in that failure, close to 270 people died, and another important part is it happened in Brazil. 15 engineers who were associated with that tailings dam were arrested, and some of the engineers are still in the they are not free, still there, because the case is still continuing in a court in Germany. And there was another incident happened in 2015, and recently that verdict came. The court fined $30 billion to the mining company because of 2015 incident, where the 2019 is much larger than the 2015. So this one definitely will be more economical failure to those mining companies. That's why the people of England, like there is a church in England, they came up with a group of people, mostly the investor group. They came up with the $20 billion was generated, and the aim is to protect most of these tailings, mainly those tailings in very critical areas. Critical areas means very close to the population or good critical structures are there. So in those areas they are focusing it and they are spending money to make sure those tailings dams are stable. So that's why all these GISTM is coming. But if you see into the failure mode, so the most important failure modes are overtopping and then slope instability, because we are making a dam there. That's like any earth dam, and these dams are very high also. Like some of the dam, they are around 500 feet height dam. So those slope failure, then internal erosion, also the external erosion, then also earthquake, where the area is earthquake prone. Compared to the hydro dam, the tailings dams are more prone to the failure during the seismic activity. And then there is a decant system which will show in our next session, how the water management. So if the water management is not done properly, then there can be a failure. That's how these failures will be important. Again, initially when people started designing the tailings dam, they thought that it's the same like any hydro dam. And even I think somebody, by discussing here, people told me that in India also people thought that it's a hydro dam, and they designed in the same principle of the hydro dam. But when it failed, people realized that yes, this has to be treated separately. So the basic difference between a tailings dam and a hydro dam we should all know, because concept is coming from there. All we are doing, seepage, stability, even water management, everything is coming similar to hydro dam. But we have to know what the difference, because that is where we will change our concept when we deal with the tailings dam. So the first thing is the stored material. The difference is in the hydro dam is the water, it's a plain water. So even if there will be a flood or it fails, so it's water only, so the flood. But here it is the solid and the water combined. So solid and water combined is more devastating than the flood, because it is charged with these sediment particles. The energy is much higher than the water when it fails. You will see that in one video. Then the operational life for hydro dam, we think that it's almost kind of 100 years. We design it thinking that it will stay for 100 years. But in the tailings, it's two things. It's not that we are designing finishing the tailings dam, but what will happen when the tailings dam is constructed, like your mining is stopped. So the next step also coming in the tailings. That's why its operational life is almost 40 years, depending on how long the mining is going on. Then the construction period, again, like the operational life is 40 years, like it takes 40 years to construct that whole tailings dam. So when we start it and finish it, it can be completely different, like the structure can be completely different. While the hydro dam, from the very beginning you design it, and then that stays for whole the lifetime. Engineering design, definitely for the water dam is considered like a very high level structure, so its design is always high. While the tailings, depending on where it is located, based on the site, it can be medium to high level design. Then the dam section, I mentioned in the hydro dam, the section is constant. You design that section, you build that section, and that section stays there. While in the tailings, the section changes with time. So that's why the main difference between the tailings and hydro dam is Hydro dam is a static structure, you can think that. Hydro dam is a static structure while tailings is a dynamic structure. That means everything is changing with time. That's the very important concept. We all have to see that. Because what we initially design, thinking this is the thing, 10 years, 20 years, things can be completely different. Then quality control and QA/QC, again, tailings varies with the site. Definitely hydro dam, we always think is very high. Then consequence of failure, I have already mentioned that. When tailings fail, it is much more devastating than the hydro. Then the closure. This is a basic difference between a hydro dam and a tailings dam. Because tailings dam has a closure. Once the mining is over, mining is stopped, we don't just leave it as it is. No, we cannot do that. Because we have to make sure after mining, this structure is safe for the environment. That's why from the beginning of the tailings dam, we also design the closure. Like when the tailings dam will get a permit, and mostly in US and Canada, when we go for the permits for the tailings dam, we have to show them this is our plan for the closure. So what the closure is, basically we put a cap on top of it, top of the whole dam. These dams are very large dams. You can see that their length is like 5 miles and width is like 10 miles. So all these structures will be capped and we have to make sure that it is environmentally safe. So this closure makes it's a completely different from the hydro dam, because hydro dam doesn't have any closure. Again, in the basic design phase, so we have like start with a concept and we have a dam. How we will start with a basic dam design, and we start with a starter dam. Any tailings dam will start with a starter dam, and that starter dam is a earth dam similar to the hydro dam, but that is a starting structure. Then during the operation, then comes the operation. That is the initial construction phase is building a starter dam. Then comes the operational phase. In the operational phase, the tailings dam is raised, and then final is the closure and also post closure. Like even if after we do the closure might take some time to do that activity, and after we finish the closure also there is a post closure period, because we have to make sure these dams are stable almost forever, but right now people are thinking they will be stable at least 400 to 500 years. So after the closure part, we will also monitor it, that is our post closure. So the basic design services, here we have 4 important players in the design of tailings dam. Can anybody guess who are the 4 important players here? Definitely the first one is the owner, because he is responsible for the construction of this tailings dam. So the owner is the number 1. Then the people who are helping them is the consultants. Then the third player is the agency, because any country, any state you go, there is an agency. Means in India also there is an agency, where when you first start you need their permission to do that. So the agency is the third player, and the contractor, because contractor is the men who will be doing everything. So these are the main four players, and these basic design services I will show you in the later part of the slide, like who is responsible for that. So mostly the historical data, any site, when we start a site, we go and collect the historical data, because that is very important, because we need to know about the site. Then we do the site characterization. Then the tailings, it's not only, it varies from site to site, because there can be different site. In a particular site it's a dry climate. Then we go to a site which is a wet climate. We go to a site which is a plain. We go to a site which is a mountain. So site can be different. Then the tailings also can be different, because so many tailings. You guys are from different industry. So most of the tailings I have dealt with is mainly the copper tailings, bauxite, some of the iron tailings. But besides that, in each mineral, like what are the other mines you think of, also they create the tailings, like coal. The coal has also the same as the tailings. Then the chromite, they can have also. So each tailings properties are different. So the way we design the copper tailings, and when we go and look into the iron tailings, can be completely different. The geochemistry is different, the geology is different, the minerals are different, and geotechnical parameters are also different. So the tailing characterization is also very important. Then that's all these things takes your planning and site selection. Then the site classification. Again, the site classification depends on where it is located. If it is very highly sensitive area or it is a remote area, things can be completely different. And we come up with the design, then start the construction, then we go to the operation, closure, post-closure, and in each stage of this design process, services, we look into the risk. The risk management also important. A lot of these things we will again cover in the later part. Then the dam failure and bridge analysis. That's a must for all the tailing facility during the permit time also. We do this dam failure because we have to show that if this dam will fail, what will be the impact to the environment. Then we establish the tailings monitoring system, and this monitoring system start from the starting to closure and post-closure also, because in the monitoring we have to show that this is stable forever, stable and safe. So there are many monitoring systems which we will cover in our courses. Then the last part is the emergency preparedness and response planning. Each tailing site should have that, because that is mostly needed at the time of failure. What you should do. So we start with a conceptual design, then we go to a pre-feasibility, then we go to a feasibility and come with the detailed design. Just one example, like how much money is spent during the design process, I can tell you. The pre-feasibility level expense is 10 million average for any particular site. That's only for pre-feasibility level. But when you go to the feasibility and detail, definitely the cost can be more and more. Again, the siting. mostly the mining, most of the mining areas, except like where the plant is, because if you consider the plant, we are coming to a plain areas, like coal plant or alumina plant. So there also you can have tailings dam in the plain areas. But in the mining areas is mostly hilly, mountainous region. So there we look into the valley, like the valley impoundment, like it can be a single cross valley impoundment, because we will take advantage of the topography here. So the valley can be a good siting, because you can see that if it is a single valley, so we have a like starter dam, then rest is the tailings dam, that the brown or red color you are seeing there, the tailings, that grey is the starter dam. And we take advantage of these valley slopes. This they protect. Or if there is multiple cross valley, you can have multiple tailings site also there. Upper level, middle level, and in the lower level. Same thing in a particular hillside. In the cross valley, you are in the middle of the two valleys. So you can have a small dam and then take advantage of that, of all the steeper slopes on the surrounding. But if it is valley, like if it is a mountain in one side, then only one side you have the mountain slope, but rest of the things you have to close it doing a, like this is single side hill impoundment. In the side, like three sides you can have this dam, and in the middle you can have the tailings. Again, same thing you can do multiple, like you can start with from the top, then go to the middle and at the bottom in the same slope. Again, similarly, again if it's a valley bottom, you can see that in the bottom side also we can have single valley bottom impoundment or multiple valley bottom impoundment. Here mainly we are taking the natural slope, taking advantage of the natural slope. If it is a mountain, one side is the slope, then definitely most of the structure will be more stable. And these are the mountainous, but when you go to the like plain areas, what we do is called a dike, ring dike. In the surrounding, you can make it a square, or you can make it a elliptical or circular, depending on how much area you have and what are the issues there. So this is a single dike impoundment, or you can also make a multiple dike, depending on how much material you can store here. This is for the plain land. So all this green is the dam, and in between grey is the pines. Again, you can have a impoundment there also, because all these tailings, not only tailings dams, they are not only storing the tailings, but also storing the water. Which water? The storm water. So in our design, we will have to also consider the storm water. So the main criteria we look into in the design is geotechnical and geological conditions. That's the fundamental and number one criteria, because we have to make sure the geology of the site is helpful. What are the subsurface conditions there, and then when we design it, what kind of dam we can design, what kind of material. So geotechnical condition of those things are very important. Then also we look into the hydrologic and climatic, because most of the hydrology depends on the climatic condition. What is the rainfall? If there is a storm water, like what is our PMP, like possible maximum precipitation is called PMP. That is mostly used in most of the design, which we will cover in the later session. Then the construction and operational factors. Definitely when you go and construct in a mining area, means mountain area, it's a different. And when you construct in a plain area, it can be different. Then seismic activity, I mentioned before, like if it is a seismically active region, you will have to consider is a very high level structure. And look into the seismic things, we will have a session also on this topic. Then environmental conditions and economic factors. So everything in mining depends on the economy. Whatever you do, money has to be there. Then the social consideration. Social consideration is very important during our planning phase, because when it fails, if there is a community close by, we have to make sure that community is not affected. So we have to look into the social factors here. Again, the tailings characteristics and their design and the regulatory requirements. Regulatory requirements varies from site to site, country to country. Like in US, we have a federal agency called EPA, Environmental Protection Agency in US. And also we have every state, we have a Department of Environmental Quality. That's the, every state we have an environmental department. Both EPA and state department will be involved in all the stages, from the planning, giving the permit, to the operation, to every stages they will be involved. These are all variables, like we mentioned, tailings are variable, site-specific are variable. Again, the mill location, definitely from the mill it is going towards the tailings. So we do not want that the tailings dam will be far from the mill, because then you will have a lot of, like you need a pipeline, and then it will be issue if there will be a leak in the pipeline. So we wanted to keep it very close to the plant. Then the topography, we saw that. Then hydrology, geology, groundwater is also very important parameter here, because we have to make sure, even when we do the tailings, where we do it, there will be always a base flow, like all the water is going to the base, and it may enter into the ground. And depending on how deep is the groundwater, there is a chance that groundwater can be contaminated. So we'll have to look into that. Then the foundation of the tailing, because these are very large structures, there is a lot of loads they are taking, so we have to make sure the foundation is good. One of the major failure happened in Canada is called Mount Poly failure, and that failure occurred because in their foundation there was a 3 feet clay layer which was somewhat ignored during the design process. Design process, they couldn't see that, or even if they saw that, they thought that 3 feet layer is okay, it will not do any more damage to our structure. But when it fell, all the experts who came up with the cause of the failure, they said that 3 feet layer was responsible. Because when that, it may be a very small layer, but if that layer fell, then all the material can go. In the design, we find all these properties. The storage capacity, site conditions, the structure, the retaining structure, that's a dam. Though we will see in the later part that dam not necessarily to be always like a earth dam, but we use also same tailings to construct the dam and same tailings to build the ponds. Then the tailing properties, the modeling. Modeling also is very important, and I can mention that right now, mostly in US and Canada, in each site, even the client wants a 3D level model for each site for all their stability analysis and seepage analysis and even the stormwater analysis and groundwater analysis, everything. They are thinking that we should have a 3D model. These are all numerical models. But in the basic design, when they started in the very beginning, always everybody followed a limit equilibrium model. In the later part, we will discuss why limit equilibrium model is now, people are not using much, but people are going to the numerical model. Structural stability, then we'll come up with the design acceptance criteria. Erosion control, because after the construction, these are all earth dams and these are all made of like fine materials. So erosion is very prominent there. Like you go to any tailing sites, erosional feature will be prevalent there. Like you will see a lot of erosional features there.
So
then the seepage, okay.
So can we ask question in between or can later?
Let us finish this, then we will have a question and answer
Okay,
session.
Then I will note down my.
Yeah, that will be good. Let us finish it. So the seepage is very important here because it will be going into the groundwater, mostly seepage. Surface water flow, and that needs also water balance. Then settlement, that's also a basic issue in most of the ponds because these are very fine materials, they definitely will settle, so how they are settling and the effect of settlement. Dust generation is a very important also because these are fines and mostly in the dry climate, the dust, they can create a lot of dust and these dust are not good for the and like any your environment or for the human life. Then the environmental factors, we will discuss that. There might be some biological impact to the groundwater. Cover and liners, that's an important topic. Right now, in US and Canada, any new structure, liner is a must. Means old structures definitely you cannot do anything, already they are developed. But any new is coming, they are making sure you have to line it. That in the, like before you start it, you line it so that the seepage or anything is fully controlled. And covers, we need that during the closure time. I mentioned you, in the closure time, you have to put a cover. And that cover is also a designed, engineering designed cover. Quality assurance, and you can have a spillway also, but most of the tailings dam, again we design it that we do not allow the overtopping. But in the wet areas, you might have a good spillway, you can design a proper spillway and again take out the storm water. You can do that. This is again, we will come back, this slide we will come back again when we discuss the tailings design. The global design will go there, but this is all the concept and we can see how they evaluate it. The environmental consideration, I want to specify or focus this slide because this is the most important slide not only for the tailings, because this slide can be applicable for any mining activity. Whether you do leach down, waste down or any transportation, everything is related, because we have to make sure due to mining the environment is not affected. Like I mentioned before, it's not we are doing it for our lifetime. We are doing it for the future also. For the future generation, we want to give them a good thing. Not that everything is polluted and they cannot do much, we have to protect that. So what are the environmental considerations? Water. We have already discussed, like we have to make sure either surface water or the groundwater is protected. Soil. Why soil contamination is important? Because soil contamination can affect also agriculture. If there are agriculture field surrounding the tailings facility, mainly we notice that in the plain areas there are agriculture fields, because you cannot find vast land just empty. So, and if there is any contamination of the soil, then your agriculture part is also lost. Then the ecosystem. We are in the mountainous region, so we'll have to look into if there is some habitats are there and they are protected, they are not affected. Air pollution, that's also very important, because it creates a lot of dust, and also those who are in the plant, also we will have to look into the plant also for some air pollutions, and we have to make sure our air part is good. And then this dam failure, we have to consider that, because when it fails, not only affect the surrounding areas, if the failure or the material goes to the river, I will show this slide, if it goes to the river, it can go further and further. Then the landscape alteration, like you can see that when we start building or the construction in the initial stage, we are changing the landscape. And then when we close it, also we are changing the landscape. So in whole evolution of landscape change, we have to make sure our surrounding environment is always same. The air is not changing the surrounding environment. Again, we mostly discuss about the slurry, but things are changing with time. I can tell you, 20 years from now, maybe we will not be talking about slurry telling anymore. So, what the next step? So, the next step is, it can be a paste or a cake. We call it, mainly the term, we call it a dry stack. And a lot of, like the bauxite mines, I think the trend, the norm is, forget this slurry, produce all the dry stacks. So, so we call it a thickened tailing and also a filtered tailing. So these are coming up very fast, and the research is going on, but still like in US, Canada, Australia, in some part of the Europe, it is still in the research stage. There is not a fully developed design for all these structures. But the thing is, if under GISTM, everything is covered. Your slurry material, because for the environmental point of view, whether it is a slurry or a dry stack, everything should be same. We have to make sure that it is not affecting the environment. And some of the dry stack I have dealt with or I have reviewed in Africa, that also failed, because these dry stack also contain 15% moisture. And if you see the vast volume, the 15% moisture is not a small thing. So that can cause also the same failure we see in this slurry dam. But definitely dry stack will be the future, because dry stack gives us more space, almost 3 times larger than the slurry. And the second thing is, definitely dry stack will be stable than the slurry, and when it fails, slurry can go and become more devastating while the dry stack won't do that much. So that's why the future is the dry stack. But for environmental point of view, we'll have to treat everything same. Come to the GISTM. And this GISTM, we had a session on it because this is very, very important. And you can see that they have a deadline. Like this deadline is whoever voluntarily agreed that by 2025 we will make sure all our structures or facilities are GISTM compliant. So the GISTM came up with the 6 factors or 6 elements of the framework: accountability, planning, risk management, change management, emergency preparedness, and review and assurance. So these are the main 6 concepts, and they have formed 15 principles based on these 6 things and come up with 77 requirements. So for each site to be GISTM compliance, we have to tick mark all the 77 requirements, which we will discuss in one session for GISTM. And the future thing, which is not yet known because it's still going on, what is happening, it will be rating. A rating is coming from our side because this GISTM is not adopted by the agency. It is coming from UNO, United Nations. But most of the, I mentioned you, like there is a Church of England, they generated investor generated $20 billion to be spent. So those investors are mainly forcing anybody who wants the investment money has to comply with the GST. So that part is also coming, where every site will be rated, and also they will rate the designers. Who will be the designers? Who will be the consultant? That so everybody, it will be worldwide. Everywhere they can see that these are the consultants, these are the designers. They are certified to do that. Okay, now, okay. So just run it. Okay, see this. Audio is kind of mute. Yeah, because you see how when this failure was happening, there was some activity, actual drilling activity was going on. It was monitored by a drone camera. So that's why they take the whole video they do. You can see how it fell, and then you look into that rail line. This rail train was going on during that time. You will see what happened to that train line also, and how it is coming. You can see that the difference between the flood and this debris flow. We call it a debris flow. How much energy it is creating. This way it is following, and you can see that there are waste dumps also on the way, and it doesn't matter. Like the whole thing is taking that. You see the video. You see how this flow is developing. How devastation it is. So those bombs or anything, waste dumps, they do not stop them. Yeah, you can see that.
So sir, this is wet slurry, right sir?
This is iron tailings. Yeah.
Along with water.
Around, this is a tailings, it's a slurry deposit.
Slurry, that is what I am asking.
Tailings and water is there.
Yeah.
Brumadinho. Yeah. It's a Brumadinho failure in Brazil. That what changed the whole tailings dam scenery. This is the after failure. You can see that bridge, the railway bridge. You can see that bridge also fell. And it went to a river, everything that went to a river. So, okay, now the lecture one we close here, and if we have some question answer. And okay.
Can I?
Yeah.
Hello. So sir, you mentioned for the design model, like one was you mentioned as a limit state and second one you mentioned as a numerical model. So I want to understand what is the difference and why we chose the limit state model. What is the difference of this model?
You know, like if you are involved in the stability analysis, any structure, whether it's a dam or a slope, mostly, like if you see in the soil mechanics book,
Yes, sir.
it's only mentioned about the limit equilibrium method, which is a very simple method. We call it a empirical method. But what limit equilibrium method do or we does, we assume that there is a failure plane. It's a critical failure plane, and we look into the physics and all the forces, and we see what is the resistant forces and what is the driving forces. And we come up with the factor of safety. And we also become conservative, and we say that the factor of safety is like your resisting forces is higher than the driving forces. So factor of safety should be higher than 1.5, that is for all hydro dams. So initially when these people started doing the tailings design, they also adopted the same thing, that we will do a stability analysis and also we will adopt like 1.5 factor of safety. But then that 1.5 also became 1.3 in some cases, because if it is a temporary. What is temporary in our operation? When we go and do the stages, it's an operational process. In the operational process, some people adopted like a factor of safety 1.3. But when it is complete, and in our closure time, when we say that whole structure is complete, is closed, it has to be 1.5. But what the difference between numerical, why we need a numerical model? Because when I started doing the numerical model, my first model, like even like a first like a project, full-fledged tailing project, I worked on a project where a tailings dam failed. And I have to develop that model, and that time 3 or 4 expertise in the world also helped me. We were as a team, and mainly it was for a litigation purpose, because it was that failure caused the client, our mining client, close to $30 million. So they found that it's mainly due to the wrong design. That's why it failed. So that's why I developed the model, and in the model we all decided that let us develop a numerical model. That time very few numerical models was there. But with the time, what we see, like I mentioned you before, that the hydro dam is a static dam. And this limit equilibrium failure is a static model also. But we see tailings dam is a dynamic. Their properties are changing. We will cover that more when we go to the issue of statistical analysis, stability analysis and seepage analysis. We will see how that is different. But what in the brief, what numerical model does, numerical model can model the dynamic condition. While this model, limit equilibrium model cannot model the dynamic condition. So limit equilibrium model can be adopted in the design stage, where you don't have, because when you start doing the design, you don't have the tailings, you don't have anything. So there you can do a simple model. But when you go to the higher and higher stages, there you need a numerical model. Otherwise, the simple empirical model cannot give you much answer.
So sir, as you mentioned, at initial stage you said that we design with a limit state, but as this properties of the slurry and the mud, the dry stack, it is dynamic property.
It is a dynamic property.
So then how we convert it from limit state method to the dynamic method?
I will cover that thing more when we discuss those stability analysis and seepage analysis and so on.
Okay.
Like how we used also numerical model and did also this stability model.
Okay. So like
It's
initially
a
you start with the
combination.
limit and then later on you convert
Exactly.
it into the dynamic
Exactly.
numerical model.
You can develop a completely numerical model that will answer all your questions.
Okay.
Or you can do a combination. Like most of the time, we do a combination of model. But right now, after this failure, Brazil failure, and with GISTM and other things, people are focusing on the numerical model.
Right.
And even not only a 2D model, because most of the things I did mostly 2D model. But now the focus is coming with the 3D model.
Right. So sir, as you said that sometimes you design it with a factor of safety considering 1.3 also. So if we keep the factor of safety 1.3, will it be safe in future or we have to go with 1.5?
1.5 is the future. Like I mentioned, 1.3 during operational time, we can do that. Like when you are going stages. For that small stage, you can assume that's a 1.3. But overall, has to be 1.5. Because when we design it, it has to be always for the closure.
Yeah, so because I am asking this question because sir, in our company, in one of our projects, we have done, already red mud ponds are there and there was some rain cuts and some cracks were observed. So we got the analysis done from the consultant and they had submitted the report in which they had shown that for in certain condition, pseudo-dynamic condition, the factor of safety is coming 1.3. So now at present the structure is safe, but will it be safe in future or like what? Because their analysis is showing 1.3 and minimum requirement is 1.5.
Again, it's all depend on it's for your own design or you are submitting that to the agency like.
No, some consultants are doing because sir, we are the owners for those red mud ponds. So we are getting it done from the consultant. So they had submitted. So they in their recommendation they said that we have to take some precautionary measures because 1.3. But as I visited the site, the red mud dam is like stable only. There are no slope failures or no the surface failure, no toe failure. But the values is showing 1.3 as a factor also.
This seismic.
Yeah.
Seismic, I will cover that also in the seismic.
Correct, sir.
Currently, we are coming up with the guideline that no more pseudostatic analysis. Pseudostatic analysis will be obsolete.
Obsolete.
Yeah.
So in that, if 1.3 is coming, we should not
Exactly.
be worried about that, right? Sir?
Yeah.
We should not be worried about that.
again, it's actually in pseudostatic we are considering 1.1 because it's a seismic. It's not regular.
Correct, sir.
It's a seismic.
Yeah.
Because under seismic you are mostly considering the residual strength, not the peak strength.
Right.
But under normal condition you are looking into the peak strength. So that peak strength should be minimum. Again, the 1.3 is a temporary
Correct.
case.
Yeah.
In a temporary case, it can be 1.3. But you have to again show that, like that's why I mentioned, in our, like in US and Canada, temporarily you can show them that's 1.3, but overall stock, because when you do it, it has to be whole thing.
Yeah.
Whole thing you have to show that it is a 1.5 factor of safety and that is maintained.
Okay. So second question is, you had mentioned one point of like water balance. So I would like to know what is the water balance study?
That water balance thing is coming in our next session in the surface management.
In detail. Okay, sir. One more question, sir. Yeah, only last question. Yeah. Sir, I would like to know the this video which had shown the Brazil dam failure. What was the reason for this failure?
There are two experts right now, like so many people work on it, but two school of thoughts. They did detailed analysis and they are coming up with completely two different criteria for their cause of the failure. One expert group thinks that the over precipitation, like the storm water, that caused the failure. Another group is thinking they were doing some drilling at the time of failure. So they are thinking that it may be the drilling. And then the same question was asked to me in a big audience, like, what is your opinion? Which is best? My answer was, if it is given to me, I can come up with a different answer. But again, I have to analyze it.
No concrete reason for that, sir.
Yeah. I do not agree with either of them.
Both.
Yeah. But again, they are good in their own analysis.
Correct, sir.
Okay, thank you very much.
Thank you, sir. Thank you.
Actually, we are running short of time for lunch, so we can carry forward the discussion after lunch.
We'll continue our discussion, and definitely I will like to interact with you people and know your own problem at your site. I think that
Okay, so we have a lot more discussion to come up. So I'll request all the participants to please go to the ETC where most of you people are staying. There we'll have our lunch. Then we come back here and at around 3 p.m. then we continue our session.
3 p.m.